Okay, so welcome to this video tutorial on Newton's universal gravitation for Regents Physics. Okay, so the question lies in that what we're asking ourselves is, what is gravity? And you know about the force of gravity at this point on Earth being the mass of the object times the gravitational field strength on the Earth. But the question lies in that what would be the force of gravity if we wanted to figure out the force of gravity between any two masses, not just your mass or an object's mass and the Earth. So we know that it's an attractive force between two objects with mass. It's important to add on there. And that the strength of the attraction, you can kind of consider that it definitely depends on the mass of both objects. And just as a reminder that the mass is got to be in kilograms. Kilograms is our base unit of mass. The distance between the objects and that is in meters. And we need to have a constant, and we call that constant the gravitational constant. Our symbols that we use for these three variables, nothing's changed here. The symbol that we use for mass is m. The distance we actually use is r, which I'll talk about why in just a moment. And then the gravitational constant, it's not little g, it's capital G. And it can be found in your reference tables. Actually, it turns out to be the first quantity of the list of physical constants. And if we put these three things together, that we can develop this equation, the F of G, the force of gravity between any two masses, is big G times the mass of the first object divided by the mass of the second object divided by the distance between them squared. Okay, so now let's just talk a moment for why we use the symbol r for the distance between the objects. So suppose we're talking about the force of attraction between the Earth and the Sun. So we know that the Earth orbits the Sun, and it turns out the distance between those centers happens to be the orbital radius of the Earth. So for large masses that orbit each other, that distance between them is their orbital radius. So by convention, we use r for the distance between the objects. And it is the distance between the centers, so you do not need to take into account the radius of each mass. So let's take a look at some examples or proportions. Often when we're talking about the force of gravity, it's useful to know how, if I change one object, how that has an effect on the other object. And we call that proportional reasoning. It shows up here, but you could apply this idea to any equation in your reference tables. So what we know is that if we look at this equation, so we'll just write this again up here, g m1 m2 over r squared. What I see is that as the m goes up, the f of g goes up in a direct relationship. So we say that it is directly proportional to the masses of the object attracted. So if I change the mass of one of the objects, so if I double and I put a 2, let's say, in front of m1, now you were taught in math class that whatever I do to one side of the equation, which in this case is putting a 2 in the numerator, that I have to do to the other side. So the end story here is that if I double m1, I double the f of g. So this would feel 2 times the force than over the original equation where we just had 1 times the mass of 1. Now if I double both of the masses, so my f of g equals g m1 m2 over r squared. So I double m1, I double m2, and likewise by changing this side of the equation, the right-hand side of this equation, by 2 for m1. I got to put a 2 in front of there. But I also put another 2 in front of m2. So I doubled the left side of the equation twice, and that is also that would work out to be 4 times the original force. So, you can consider that if the original force in this first example was 10 newtons, if I double one of the masses, my new force would be 2 times that, or 20. Likewise, in the second example, if my original force of gravity between 2 objects was 10 newtons, my new force, when I double both masses, would be 40 newtons. So this is a proportion of how much bigger or smaller. In this case, both of them were bigger. Now, what you notice is that in the r is in the denominator, so as r goes up and you divide by a bigger number, what you will see is that the force of gravity goes down. But it doesn't go down by the same factor since r is squared, which we'll talk about just in a moment. The force of gravity is inversely proportional to the square of the distance between the objects. So in other words, what we call this in a more mathematical sense is the inverse square law. And we will see this a couple more times throughout the year, that if r goes up, as r goes up, f of g goes down. And so it looks very similar to a typical inverse graph. So we're saying it follows the equation y equals 1 over x squared. And you could check this in your calculator. It looks very similar to y equals 1 over x, just the only difference is the rate of change is steeper, meaning that if you had an inverse graph, you might see it a little bit more gradual. But there will actually be an intersection, so that might not be entirely accurate. So I'm going to keep that. They would intersect at 1, 1. Because 1 over 1 is the same as 1 over 1 squared. All right, so let's take a look at some conceptual examples here with the proportions. So if I double the distance, so my f of g equaling g m1 m2 over r squared, if I'm doubling the distance, that means that the 2 objects are getting further apart. I know that my force of gravity should get smaller, because that conceptually makes sense. But I'm not just getting smaller by a factor of 2. In other words, I'm not just dividing by 2. Since my r is squared, I'm really changing this side of the equation, the right-hand side of the equation, by 2 squared. So, once again, whatever you do to one side, you have to do to the other. So I'm going to divide the left-hand side of the equation by 2 squared, which is also my equal to 4. So if I double my distance, I actually turn out to quarter my force. And that is the nature of an inverse squared relationship. You change one side of the equation by some factor, you change the other side of the equation by that factor squared. So if I triple my distance, g m1 m2 over 3r squared, then what I would see is that this side of the equation would go down by a factor of 3 squared, or 9. So my new force is 1/9 the original value. Now, the tricky part is, and you'll see this on the next page, is what to do when your distance gets smaller. So, in other words, your objects get closer together. So, if, let's say my r goes down by a factor of 2, the new distance is half the original distance. So, I know that this factor is going to go up, okay, because if 2 objects are close together, it seems logical that their force of gravity is larger. But it's not simply, once again, just be a factor of 2. If r goes down by a factor of 2, f of g is going to go up by a factor of 2 squared. Okay, so just like in our first example over here, that the distance doubled and the force of gravity went down by a factor of 4, if the distance gets cut in half, my force of gravity is going to go up by a factor of 4. Okay, so what I'd like you to try to do is go through these examples and use the same step that we did on the previous page. We actually already did this and this one this one as well. Okay. Go through and see how your new force would change if you do what is directed. So, what I would like you to finish up for the remaining of the homework is come up to here, and what we will do is we'll chat about what proportions you found for these various examples. Okay? So, thanks for listening. I hope you have a good night, and we will see you tomorrow. All right. Good night. Bye.